Hello guys, in this video I'll talk about how you can find Jacobian in Mathematica. So let's look at this problem. Solve for x and y in terms of u and v and then find the Jacobian j of uv. So you have to find the partial derivative of x and y with respect to u and v and find the determinant of the Jacobian matrix where the transformation is u equals to 2x minus 5y and v equals to x plus twice y. So let's find x and y in terms of u and v. So we can solve the equations. So u equals to 2x minus 5y and v equals to, so you have to use double equal sign, v equals to x plus twice y, and we want to know x and y. So we have got the expression for x and y in terms of u and v. Now we can find the partial derivative of x and y with respect to u and v. So let's just define our x and y. So x equals to 1 by 9 2u plus 5v. Give a semicolon. I just want to define x, and y equals to 1 by 9 2v minus u. So x and y are defined. Now let's see how you can find the Jacobian. So we know how you can find the partial derivative. We have to use the partial derivative sign d, and inside d I can write x and y. I have already defined x and y, so let's just give a list, and inside the list write x and y, x comma y, and now you have to give double curly braces. So remember, you have to give double curly braces to find the Jacobian. So inside the double curly braces, write uv. U and v are our variables, and close the square bracket. So x and y are defined. So Mathematica will substitute the value of x and y. Now if we give double slash and write matrix form, we'll get the Jacobian matrix. So here you can see that we have dx by du, dy by du, dx by dv, and dy by dv. This is the Jacobian matrix. But we are interested in finding the determinant of this matrix. So to find the determinant, I don't have to write the matrix form. So let's just delete the matrix form. We have to find the determinant. So write determinant det with capital D, and give a square bracket, and inside the square bracket give the whole thing, and if you press shift enter now, we'll get the determinant of the matrix. So this is the Jacobian of our transformation. Let's solve a problem from the practice sheet. Starting from Cartesian coordinates described in spherical coordinates, use the Jacobian determinant to prove that for spherical coordinates dv equals to rho square sine theta d rho d theta d phi. You know that dv is dx dy dz in Cartesian coordinate. So the multiplication factor here is rho square sine theta. So if we just prove that the Jacobian of the transformation is rho square sine theta, we can say that volume element is rho square sine theta d rho d theta d phi in spherical coordinate. Let's just delete the variables from the last problem. These are the transformation from Cartesian coordinate to spherical coordinate. Here in the transformation, I have chosen phi as the angle with z axis, so I'll get rho square sine phi from the Jacobian. If I had chosen theta as the angle with z axis, I would have got rho square sine theta. So let's just define x, y, and z. Now I can easily find the Jacobian. So inside the list write x, y, z, and give double curly braces, and inside the curly braces write the variables. First row, so write escape button rho, escape button to write rho, and then theta and phi. So if you want to see the matrix form of the Jacobian matrix, give double slash and write matrix form. So this is the matrix form. I want to find the determinant of this matrix. So write det with capital D, and inside the square bracket keep the whole thing. And if you press shift enter now, I will get the expression. Let's just simplify this expression. So write simplify and give percent sign. Percent sign indicates the last output. So we get minus rho square sine phi, and we'll have to take the absolute value of this.